Let's solve some questions. These questions on order of elements, subgroup, cyclic group, subgroup generated by an element. So on these topics, we will solve some questions. So these questions we have already done. I told you how, okay, this question, and I think this question we have done. This was homework. Did you do? The subgroup generated by 5 in U18. Did you do this? In this U18, this question number H. So you have U18. First of all, what is U18? That is 1, 2, 3, 4, 5. Okay. Then that will be 6, 7, 8, 9, 10, I think 11, and then I think, okay, so 13 and 17, right? This is a U18, correct? So in U18, what is the subgroup generated by 5? What, okay, did you try this? What is the operation? What is the operation that comes with U18? With U18, this operation comes, okay, multiplication modulo 18. This is the operation. So tell me, what is the subgroup generated by 5? Because this is a finite group, you can notice this is a finite group. So do you need to go in the negative direction? See, because this is a finite group, you already know this is a finite group. So because this is a finite group, so to calculate this subgroup generated by this 5, do you need to go in the negative direction? You don't need to go in the negative direction because this is a finite group. So I can say that you will definitely get identity element. Definitely somewhere you will get identity element. Okay, so you can start with 5 power 1. 5 power 1 is 5. What is 5 power 2? That is 5 multiplied by 5 and mod 18. Remember what is 5 power 2? That is 5 multiplied by 5 and then you find mod 18. So that will be 7. And what will be 5 power 3? 5 power 3. Okay, so 5 power 3, that there you can find like this. Now you don't have to work. Remember 5 power 18. That means 5 square, okay, multiplied by 5. And you already know this is your 7. This is your 7. So that will be basically 35 mod 18. And that is 17. Right? So like this. Okay, so you don't have to calculate again. Don't calculate again. Save some time. Don't calculate again. So tell me, what will be 5 power 4? 5 power 4. What that will be? That will be 5 power 2, 5 power 2. This is 7. This is 7. 5 power 2. You already know this is 7. This is also 7. So that will be 49 mod 18. Okay, and that is, I think that will be 13. Okay, so that will be 13. And what will be 5 power 5? So 13. This 13 multiplied by 5 mod 18. 13 multiplied by 5 mod 18. So I think this will be 11. Okay, and what is 5 power 6? What is 5 power 6? 5 power 6, that means 11 multiplied by this. So this will be 1. And this is your identity element. So here you can stop. At this point, you can stop. Okay. So tell me, what is the inverse of 5? How will you find inverse of 5? Here you stop. So this will be the inverse of 5. This will be the inverse of 5. So inverse of 5 will be 11. Very simple. Okay. So can I say this 5 is a generator? Can I say this 5 is a generator? Because it has generated how many elements? The order. This is the order of 5. This number is the order of 5. So 6 element is it has generated. Okay, so you can notice that this is order of 5. This number is order of 5. It means how many elements this 5 has generated. So this 5 has generated 6 elements. And we total have 6 elements. Yes. So 5 has generated 5, 7, 17. Okay, 13, 11, 1. All of them you have generated. So 1, 5, 7, 11, 13, 17. So I can say that. So what I can say? So I can say 5 is a generator. So 5 is a generator. Okay. And you know that 5 inverse is what? 5 inverse is 11. So 11 is also generator. 11 is also generator. I can say that 11 is also generator. Because 5 inverse is 11. So I can say that this 11 is also generator. Okay. So very simple. And order of 5. What is order of 5? What is order of 5? That will be the cardinality. How many elements 5 has generated? I can say 5 has generated 6 elements. Okay, so this 5 has generated 6 elements. Has generated 6 elements. Okay, so I can say that order of 5, that means how many elements it has generated, that is 6. How many elements it has generated, that is 6. Or I can say what is the minimum, what is the smallest, 5 power, what is the smallest, such that you get identity element. Okay, so this is smallest, so this is the smallest, I can say this is the smallest positive integer, such that you will get identity element. So I can say this 5 is a generator. So what can I say about, because this 5 is a generator, so what can I say about this U18? What can I say about this? What is this? This U18 is a cyclic group. This is a cyclic group because it can be generated by single element. This element 5 can generate this U18. So this is cyclic because there exists a generator. And one interesting thing, okay, remember this is a cyclic group. You know that U18 is a cyclic group. So I can say that this U18 is 157, 11, 13, and 17. Okay, so now you check, because 5 is a generator. You know that 5 is a generator. So this same thing I can write like this, because this is a cyclic group. You know that this is a cyclic group. And who is the generator? The generator is 5, 11. You can check something else. Can I say something else is a generator? Check it out. 5, okay, is 7 a generator? Tell me. Is 7 a generator for this U18? This is your U18, 157, 13, 11, 17. What, okay, can I say 7 is a generator? What 7 will generate? 7 will generate 7 power 1, that is 7. 7 will generate 7 power 2, that is 13. Okay, because operation is this. And what is 7 power 3? What that will be? Check it out. Take your calculator and check it out. Is it 1? Okay, so because you got identity element, okay, so that is the reason I can say you can stop here. So what is the order of 7? This number is the order of 7. This number is the order of 7. I can say order of 7 means how many elements it has generated. 7 has generated 3 elements. And what is the inverse of 7? This number is the inverse of 7. Here you can find the inverse of 7. So 7 inverse is 13. So how many elements 13 will generate? 13 will also generate the same number of elements. So order of 13 also will be 3. The same elements will be generated by 13. Okay, so I can say that these same 3 elements will be generated by 13. Okay, so I can say that 7, 13, these are not generator. What about 17? Is this generator? So 7, 13 not generators. These are not generators. And what about 17? Is 17 a generator? What will happen with 17? So you will get 17 power 1. What is 17 power 2? 17 power 1, that will be 17. And finally you will get this. So you can notice that this number is your order. So how many elements 17 has generated? So the number of elements 17 has generated, that is order of 17. 17 has generated 2 elements. Okay, and so this number is your order of 17. This is your order of 17 because this is your identity element. And what is the inverse of 17? This will be the inverse of 17. This will be your 17 inverse. So I can say 17 is not a generator. I can say 17 is not a generator. So finally, I can say what are the generators for this U18? Only 5, 11. So only 2 generators you have, 5, 11. So 5 is a generator and 11 is a generator, 2 generators you have. So now you can notice, because it is a cyclic group, so I have another way, because these are generators. So I can also write this cyclic group as 5 power 0, 5 power 1, 5 power 2, 5 power 3, 5 power 4, and 5 power 5. Right? Yes or no? Correct? These two things are same. You can check it out. And I can also write like this: 11 power 0, 11 power 1, 11 power 2, 11 power 3, 11 power 4, 11 power 5. Okay, so these are the 2 ways. Correct? So I can, all of them are same, remember. And the operation, of course, operation is same. Operation is same, multiplication modulo 18. Of course, operation is same, multiplication modulo 18. Okay, so because it is a cyclic group, this is important thing that I want to tell you. Because this U18 is a cyclic group, so you can write this U18 like this. Of course, operation is same. Operation must be same, So this is the idea. This is 5 power 5. This is not 5 power 6. 5 power 6 is 1. You can just check it out. 5 power 6 will be 1. Or you can do like this. You can just remove it and you can write 5 power 6. That is also correct. This is also correct. Okay, so basically this is also correct. You can write it 5 power 1, 5 power 2, 5 power 3, 5 power 4, 5 power 5, 5 power 6. This is also correct. There is no problem. This is also correct. All of them are same. So this we have done, right? And this we have done in the last class. And this is important because here you can notice this is an infinite group. This is an infinite group. And what is the order of this element? What is the order of this element? We have found this. What is the order of this element in the last class? That was 8. Okay, so that was it. Now you can notice this is an infinite group, but the order of element is finite. Okay, and did you try all of them? The remaining? Did you try? Like, did you try this question? This question we have done. And did you try this? This one, did you try? The subgroup of C star generated by iota. So you can notice if you have this structure, C star and multiplication. Remember what is C star? These are complex numbers. Remember, these are complex numbers, non-zero complex numbers. C star means non-zero complex number. What is a complex number? Complex number basically involves iota. It is like something a iota by a iota plus b. For example, 5 iota plus 10. For example, 5 iota minus 10. For example, 5. Every real number is also complex. Okay, every real number is also complex. Not that every real number is also complex. Every real number is also complex. So complex number is something like this. Here this is real and this is also real and you have iota. Okay, so basically this type of number is called complex number. This type of number, is this clear? A iota plus b, this type of number is called complex number, where a is real number, b is real number. For example, 5 is real number, 10 is real number. Okay, so this is also, and for example this is also, for example this is also, all of them are complex numbers. Okay, now the complex number definition is very simple. So complex number means you have something real number multiplied by iota and plus some real number. Okay, so this is the definition of complex number. Anyway, and now what is the subgroup generated by iota? Here, what is the subgroup generated by iota? What that will be? So that will be, because this is an infinite group. This is an infinite group. So tell me what will be iota power 1? That will be iota. What is iota power 2? That will be minus 1. What is iota power 3? That will be minus iota. And what will be iota power 4? That will be 1. And that is your identity element. Because your operation, infinite group. This is an infinite group. And you also know the identity element. Identity element is 1. So tell me, do I have to go? Just tell me this point. Do I have to go in the negative direction? Once I got this, once I get this E I got. Once I get this, now this will be my order. This is the order of iota, I can say. And this will be the, and you know, this will be your iota inverse. This will be your iota inverse. How many elements this iota has generated? What is the order of iota? Iota has generated total 4 elements. So this is the order of iota. Iota has generated total 4 elements. This is another example that this is an infinite group. This group is infinite, but the order of iota, this is an infinite group, but the order of iota is 4. Okay, so like this you can do. I hope all these questions now you can do. Okay, so this also we have done. Now the remaining questions I will not do. You can do and you can discuss on the Telegram group. You can discuss. Okay, so just check it out. Like find the order and all these things. Let's solve this question. Quickly tell me what is the answer. The question is asking order of identity element. So tell me what is the order of identity element? The order of identity element is always 1. For every group, whatever group you take, the order of identity element will always be 1. Because identity element can only generate identity element. Okay, I can say E power 1 is equal to E. And you can notice this is positive. And this is smallest positive. You can notice this is smallest positive. This is the smallest positive integer. E power 1 is equal to E. Okay, so that is the reason I can say the order of identity element is always 1. This will always happen. And what about this question? B is an element. Can I say order of B is equal to order of B inverse? Can I say element has the same order as its inverse? Yes, yes, definitely, because you know that, okay, what is this? This is B power integer. This is B power integer. You can see that this is B power integer. And what this is, and what this is also B power integer. I can write, okay, this means B power minus n, where n is integer. Or I can write like this. Actually, both are same. You can check. Both are same. Because this is also B power 0, B power plus minus 1, B power plus minus 2, okay, B power plus minus 3, and so on. And you can notice this is also B power 0, B power plus minus 1, B power plus minus 2, B power plus minus 3, and so on. So both are actually same. So what you can say, okay, what you can say that this or this subgroup generated by B is same as subgroup generated by B inverse. Both will generate the same subgroup. Okay, so subgroup generated by B, subgroup generated by B inverse, that will be same. So I can say their order is also same, because order is size of this. What is order? Order is size of subgroup. Okay, so I can say, remember this is a note that for any B, for any belonging to group G, I can say that subgroup generated by B, okay, this is same as subgroup generated by B inverse. Also, you know, because this is happening, so I can say that order of, so number of elements in this, that is same as number of elements in this. So basically I can say that order is same. Okay, so order of B is same as order of B inverse. So that is the idea. Every element has the same order as its inverse. This is another question. If G is a generator, now remember G is a generator, then can I say inverse of G is also a generator? G is a generator, then can I say inverse of G is also generator? The answer is yes, because you know that for any element, whatever element you take, okay, for any element A, what will happen? That subgroup generated by A is same as subgroup generated by A inverse. But you can notice that because G is generator, because G is also a generator, G is also a generator. So what I can say? Because G is a generator, so what I can say? I can say that it will be same as G inverse, and this will be same as G. Agree? Because this G is a generator, so it will generate all the elements. So because this is generator of G, so I can say that this will be equal to G. Okay, agree? So remember, if G is a generator, then its inverse is also generator. Okay, let's solve this question. For a finite group, if order of A is same as order of G, then can I say A is generator? For a finite group, if order of element is same as order of group, yes, because you have a finite group, so the answer here is also yes. Remember, you have a finite group, your group is finite. Okay, because your group is finite, and this question is saying that A belonging to G, such that order of A, the question is saying that order of A is same as order of G. It means, what it means, can anyone tell me what it means? Order of A is same as order of G, and order of G is equal to number of elements in G. Number of elements in G. What it means? It means A can generate all the elements. It means A can generate all the elements, because you can notice the order of A is, so A can generate all the elements. I can say A can generate all elements. All elements of G. A can generate all the elements of G. So remember, for a finite group, this will happen. This will not happen for infinite group. For a finite group, this will happen, that order of A equal to order of G. Order of G is nothing but number of elements in G. So this A can generate all the elements of G. So I can say this A is a generator. So because order of A is equal to order of G, Okay, and remember this is a finite group. This is important because this is a finite group. So I can say that A is a generator. Okay, so A is the generator, and automatically A inverse also will be generator. So automatically this A inverse will also be the generator. Tell me about this one. Infinite group you have. There is an infinite group G. If order of A is infinite, then can I say it is generator? If order of A is infinite, then can I say this is generator? The answer is no. What is the example? Anyone want to give me example? Example is, you can take this group, set of integers, comma, addition. You can take this group. And you notice what is the subgroup generated by 2? Tell me, what is subgroup generated by 2? Subgroup generated by 2 is all the even numbers, all the even integers. Subgroup generated by 2 is all the even integers. So you can notice this is not same as G itself. This is not same as G. So order of 2 is infinite. You can notice. So I can say order of 2 is infinite, but you can notice that this 2 is not a generator. But 2 is not a generator. Okay. So remember, for a finite group, this will happen. In a finite group, if you have this, okay, in any finite group, if you have this, then this will happen that A is a generator for a finite group. But you can notice for infinite group, this will not happen. You can take this example. So order of 2 is infinite. 2 can generate infinite number of elements. 2 can generate all the even integers, but 2 is not a generator. Okay, let's move on. All these are very small questions, very simple questions, but all these are important. Okay, so let's solve this question. You have a group G. A is an element of G. What is the definition of subgroup generated by A? This definition I want. So tell me some options I am giving you. Some options I am giving you. A power integer. A power integer. Okay, so some options that I am giving you. A power integer. I'm okay. Another option I am giving you. A is natural number. Another option I am giving you. A is whole number. A is whole number. A is whole number. So tell me which option is correct. Fourth option I can also give you. Fourth option I can give you is this is equal to a power minus n, where n is a power minus n, where n is whole number. Okay, where n is natural number. Okay, so some options you have on your screen. So which is correct definition? Which definition is correct? Okay, you have a group. In this group, if these things you have some element, then which definition is correct? Okay, what is the reason? Tell me why this definition is not correct. Because this group can be infinite also. I told you in the last class, this definition is correct. These definitions are not correct in infinite groups. These definitions are not correct. These definitions are not correct for infinite group. Yes or no? Because this group, okay, so this definition is correct, means all the integer powers. But tell me, the same question I am asking you, but for finite groups. For finite group, tell me. For finite group, now tell me, if you have a finite group G, then what is subgroup generated by? What is a subgroup generated by A? I am asking subgroup generated by A. Yes, now this is also correct. This is also correct. All of them are correct. Now you can notice this is also correct. This is also correct. This is also correct. This is also correct. Because remember, you have a finite group. So you can start from 1 and then you can go till identity element. The idea is very simple. To find this, if you want to find this, then what will you do? Tell me. What will you do? You will start from 1 and you will go till identity element. Once you get this identity element, you will stop here. Once you get this identity element, you will stop here. and this will be your order of A. This will be your order of A. Okay, so this will happen for the finite group. And what can I say for the infinite group? For the infinite group, because only this definition is correct. These definitions are not correct for an infinite group. I told you example in the last class. Do you remember? One more question I want to ask. Let's assume you have infinite group. Let's assume you have infinite group. Okay, but you have some element whose order is 10. Let's assume you have some element whose order is 10, whose order is, for example, maybe 5. Then what can you say? Means whose order is 5. Then what you can say? Then what can I say about this? Tell me. Because order is 5, what it means? Tell me, order is 5, what it means? It means a power 5 is equal to E. It means a power 5 is equal to E. And this 5 is the smallest. This 5 is the smallest positive integer. This is the smallest positive integer. Okay, so I can say that in the subgroup generated by A, remember, this is the subgroup generated by A. So in this, you will have total 5 elements: A power 1, A power 2, A power 3, A power 4, A power 5. These 5 elements will be there. Agree or not? Okay, so these 5 elements will be there. And you know, here you will stop. At this point, you will stop. And what is this? What this will be? This will be A inverse. This will be your A inverse. Okay, so this is the idea. In infinite group, if some element has order, some natural number, I can say, means some natural number if you have, if order of A is some natural number, then what can I say about this? This will be A power 1, A power 2, and so on, A power n, because A power n is equal to E. And this is the smallest number. And this A power n minus 1, this will be your A inverse. Okay, and this will be your order. This is your order. Is it clear? Is this point clear to everyone? So if you have an infinite group, but this element has order, some natural number, some positive integer, then I can say that subgroup generated by A, that will be A power 1, A power 2 till A power n. Or I can say A power 0 till A power 0, A power 1 till A power n minus 1. This is also correct, because this is same as A power 0. Okay, remember, this is same as A power 0. This is same as your A power 0. So I can also write A power 0 till A power n minus 1. Is this clear? This is also correct. This is also correct. Both are correct. If you have a finite group, G, then can I say that order of any element, can I say order of any element is definitely less than equal to order of group? Can I say? Arey, what is this? First you understand this. This means, can I say this? First you understand this. Answer is yes. But understand this. What this means? Anyone want to tell me what this means? This means how many elements A can generate. This means number of elements that A can generate. Yes or no? Number of elements that A can generate. Agree or not? So use this definition. This means number of elements that this A can generate. How many elements this A can generate? Tell me, how many elements this A can generate? It will definitely from 1 to maximum these many elements you can generate, right? Yes or no? Maximum you can generate these many elements. Maximum you can generate all the elements of G. Okay, and this is the number of elements in G. This is the number of elements in G. So are you getting my point? Is this point clear to everyone? Number of elements that A can generate. So A can generate, how many elements A can generate? This will be from 1 to cardinality of G. Okay, so you can say that for any group, I can say that for any group, you can take any group G you take. Okay, then in that case, these points I can say, order of any element that will be less than equal to order of G, and that will be greater than or equal to 1, because at least one element it will generate. Tell me, if A equal to 1, if A equal to identity element, then what can I say? Then order of A equal to 1. And if A is not equal to identity element, then what can I say? Then what can I say? Then it will be 2, at least 2. Yes or no? Then at least 2. Because if A is not identity element, then it can generate E comma A. Definitely E comma A it can generate. So from 2 because of E comma A. Is this clear to everyone? So this 2 is coming because of E comma A. So in general, for all A I can say this. For identity element I can say this. And for all A which is not equal to E, for them I can say this. Tell me, is this thing clear to everyone? Is this concept clear to everyone? So now you can notice, while creating subgroup generated by an element, okay, while creating subgroup generated by an element, inverses are only needed. That you have to go to negative side only if group is infinite. If you have a finite group, then inverse of element can be expressed as positive power of that element. This line is important. This line, can you notice this line? Is this correct? Is this statement correct? This statement is correct, because if you have a finite group, remember, if you have a finite group, then I can say that A inverse, this can be represented, this A inverse for all A, I can say that for all A belonging to G, what I can say that this A inverse can be represented as what? This A inverse is equal to, this A inverse can be represented as some positive power. Okay, A inverse can be represented as some positive power of that element. And what that positive power will be? That positive power will be n minus 1. Okay, where n is the order of, where n is the order of A. So this is the idea, very simple. So remember, for finite group, this A inverse can be represented like this. A inverse is equal to A power n minus 1, where n is the order of A. You can also think like this. You can also understand like this. N is order of A. What it means? What it means? It means A power n is equal to E. Now what you do? You multiply by A inverse. Now you multiply by A inverse on both sides. Multiply by A inverse on both sides. What will you get? What will you get if you multiply by A inverse on both sides? You will get A power n minus 1 equal to A inverse. Okay, and order of any element is positive, you already know. Okay, in any group, whatever group you take, for all A, what will happen? Order of A, that is the smallest, this will always be positive. This will always be a positive integer. This will always be a positive integer because this, we define this as smallest positive integer. This is the definition, smallest positive integer, and such that smallest positive integer and such that A power n is equal to E. So this is the definition. So remember, this is always a positive integer. Or you can think like this, how many elements? This means A can generate how many elements? Can A generate negative number of elements? Is it possible? Just think about it. Is it possible that A can generate negative number of elements? No. So this is the number of elements generated by A, and that must be positive integer. This is number of elements generated by A. Generated by A. So of course, this number of elements that is generated by A, this should be a positive number. Okay, so this is the idea. I hope all these concepts are clear. Are they crystal clear? I hope, like, these concepts, are they crystal clear to your mind? Like, okay, all the variations, they can ask you anything. So all the things, all the small things I'm telling you, these two concepts, you understand the difference. Okay, you have a group. Okay, I am not talking about subgroup. I am saying subgroup can be anything, and I am talking about subgroup generated by an element. These two things are different. Subgroup by an element, generated by an element. Is this clear? Okay, just understand this point. For example, subgroup, this concept is different from subgroup generated by, yes, of course, this is also a subgroup, but this is a special type of subgroup. I told you this is a special type of subgroup. Yes or no? This is a very special subgroup. So please understand the difference between subgroup and subgroup generated by an element. I am talking about subgroup generated by an element. For example, like you can give a subgroup which is not generated by an element. For example, let me give you, you take this group G equal to U18, U8. Take this group. Okay, in this group we have 1, 3, 5, 7. This is your group. Now tell me, now note, can I say G is a subgroup? Now tell me, can I say G is a subgroup of G? Can I say G is a subgroup of G? Yes, G is a subgroup of G. But can I say G is generated by some element? Can I say G is subgroup generated by some element? Can I say G is subgroup generated by some element? Some element. Tell me. Just think about it. See, G is a subgroup. Yes, this is a subgroup. But can I say that G is equal to subgroup generated by some element? Can I say this is subgroup generated by some element? The answer is no. The answer is no. There is no element which can generate this subgroup. This subgroup cannot be generated by any element. So remember, this G is a subgroup, but remember, this is not a subgroup generated by some element. Is this clear to everyone? So please make sure this, I am talking about this very special subgroup, very special subgroup, subgroup generated by an element. This is what I'm talking about. I'm not talking about subgroup. You already know the concept of subgroup, you already know. So this G is a subgroup, but this G is not a subgroup generated by some element. Is this clear? Okay, let's move on and let's see this question. So tell me the answer. Any group G, G is an element such that order of G is equal to n. Then can I say subgroup generated by G is finite? Order of G is n. Yes, of course. Yes, of course, because you are saying that order of G is equal to n. This automatically means what? This automatically means what? Tell me. This means number of elements generated by G is n. This means number of elements generated by G is n, means this order of subgroup by G is n. Remember, order of G is n. It means what? It simply means that these are the number of elements it can generate. So it means that number of elements generated by G, that is n. Okay, let's see this question. Any group you have, then tell me G is an element and order of G is equal to G. Then can I say that these are distinct? Tell me this question. So you have any group you have, whatever group you take, G is an element such that order of G is n. Order of G is n. Then can I say these powers are distinct? Yes, these powers will be distinct, right? Okay, so this statement is correct because you are saying that order of G is n. Order of G is n. What it means? It simply means that you have G power 1, G, or I can start with G power 0 also. I can say G power 0, G power 1, G power 2, and so on, G power n minus 1. Okay, so this will be the subgroup generated by G. We have already seen this. Okay, so if order of G is n, then it automatically means that this is the subgroup generated by G. So how many elements this G will generate? N elements are generated by G. Okay, so you can notice that these N elements are generated by G. So I can say these are distinct. Is this clear? So these powers will be distinct. I can also say that these powers will be distinct. I can also say that if order of G is N, then what will happen? These powers will also be distinct. G power 1, G power 2, G power 3, and so on, G power N. Right? Yes or no? These also will be distinct. So these powers will also be distinct. Because this is same as what is the subgroup generated by G. But you can notice these will not be distinct. If you notice, if order of G is N, then can I say these power will be distinct? G power 1, G power 2, G power 3, and so on, G power N, G power N plus 1. Can I say they are distinct? Can I say they are distinct? Tell me, if order of G is N, then can I say they are distinct? The answer is no, because what is this? This is same as G power 1. Okay, so this is same as G power 1. So the idea is that these are not distinct. Okay, so this is the question, that if you have some element and order of G is N, then can I say these powers will be distinct? Yes, these powers will be distinct because these will create the subgroup generated by G. Okay, these will create the subgroup generated by G. Let's see this one. If you have any group, G is an element, then for some distinct integer m comma n, let's assume, then can I say G is finite? Okay, read this question and tell me what is the answer. G is an element, and we are saying that for some distinct integers m comma n, G power m is equal to G power n. Then can I say order of G will be, can I say this will be a finite set? Number of elements generated by G, that will be a finite set. What do you think? What do you think? The answer is yes. The answer is yes. Why? This is any element. This G is any element. I am not saying G is a generator. I am not saying G is a generator. I am saying G is any element. And if G power m equal to G power n, then can I say subgroup generated by G is finite? This is the question. So notice that, okay, just tell me, this is the idea. Idea is this. Just notice that, let's assume some element you have, let's assume, such that let's assume a power 7 is equal to a power 10. Let's assume. Then what it means? Tell me, if a power 7 is equal to a power 10, what it tells you? It tells you what? A power 7 is equal to a power 10. Remember, it tells you that a power 3 will be identity element. This will tell you that a power 3 will be identity element because a power 10 is a power 7, a power 3, and that is same as a power 7. A power 10 is same as a power 7. So from here I can say that a power 3 will be identity element. Yes or no? Is this clear to everyone? So this idea, is this idea clear? So you can notice that if you have distinct integer m comma n, so if you take any group, okay, remember any group you take. So you take any group, whatever group you want, you can take any group G you take, and for all this can be any element. Now, so let's assume that m is not equal to n, and I'm saying that a power m is equal to a power n. Then what can I say? Then what it implies? Then what it implies? It implies that a power m minus n, this will be identity element. Yes or no? Correct or not? It means this will be identity element. I can say this also will be identity element. Okay. So I can definitely say, what I can say, I can definitely say that order of this element will be definitely finite. So I can say order of A. So I can say order of A is definitely finite. Yes or no? Is this clear to everyone? Because you are getting identity element. Because you are getting identity element, so order of A is definitely finite. Is this point clear? Let me know if there is any doubt. See, the okay, this is the idea. I am just telling you the idea. A power 10 I can write like this. Okay, and I can say that a power, and this is same as a power 7. This is given to you. So I can say a power 3 is identity element. Now you can notice that if you take any group, any element, if this will happen, then I can say that a power m minus 1 en, that is identity element. It's like this. For example, this C star comma multiplication. Let me take this C star comma multiplication and take this iota. This iota belongs to G, right? Yes or no? Correct? Yes or no? Agree? So iota belongs to G. Can I say, tell me, you can notice that 16 is not same as 20. Agree? 16 is not same as 20. So this is your M, this is your N. But you can notice that, or maybe I can take 28, or maybe I can take 28. So you can notice that this is your N, this is your M. Can I say 2 iota power M is equal to iota power N? Can I say this? Iota power 16 is equal to iota power 28. Can I say? Yes, agree? Yes, correct. So what it means, from this you can notice that you know what is iota power 28. Iota power 28 I can write like this. I can write like this I can write. Okay, and this is same as iota power 16. So this iota power 20 I can write like this, and this is same as iota power 16. This is a group, so you can cancel them out. So what I will get iota power 12 is equal to identity element. Okay, what I can say? I can say iota power 12 is identity element. So I can say, what can I say about order of I? So what can I say about order of iota? What can I say about order of iota? Order of iota means smallest. Remember, iota power 12 is E, but order means smallest number. This means smallest integer. This means smallest positive integer. Such that this means smallest positive integer such that a power n, I power n is equal to identity element. Okay, so this is the idea. So I can say order of I is definitely less than equal to 12. Agree or not? Yes or no? Is this clear to everyone? I can say order of I is definitely less than equal to 12, because remember, order means smallest. Order means smallest. Okay, so order of I will be definitely less than equal to 12. In worst case, it can be 12. In worst case, it will be 12, but I can definitely, because this is smallest. So I can say order of I is less than equal to 12. And what is the order of I? Actually, what is the order of I? That is 4. Order of I is actually 4. So I hope this concept is clear. So what I am saying that, so from here, what you can say? So it means order of A, that is less than equal to, because one of them is greater. Both are different, right? See, both are different. What it means, one of them is greater. Both are different. So let's assume one of them is greater. Both are different. It means one of them is greater. Then tell me, what can I say? I can say order of A is less than equal to n minus m. Sorry, order of A is less than equal to m minus n. This is the note you can take. Any group G. Okay, remember, any group G, and this can be any element. This can be any element. If m comma n are different integers, if m comma n different integers, and a power m is equal to a power n, then it means a power m minus 1 is identity element. A power n minus 1, this is also identity element. Okay, it means these will be the identity element. And I can say order of A. So order of A, that will be less than equal to m minus n. Okay, so these are different integers. Let's assume if m is greater than equal to n, if m is greater than n. Okay, so these are different integers. Then, and if this happens, then I can say order of A will be less than equal to this. Okay, is this clear to everyone? So this type of question, like this is a very simple question. Can you notice? This question is not very hard. this is given to you, and from this you can see these are distinct, these are different. So you can consider this type of example, you can consider. So I can say that a power 3 will be identity element. So it means, so I can say order of a will be basically less than equal to 3. Agree or not? Order of a will be less than equal to 3, because a power 3 is identity element, so I can say order of a is less than equal to 3. So that's the idea. And what about this one? A group you have, okay, this is the contrapositive. Is this true statement? Any group you have, whatever group you have, G is some element, G is any element. If this is infinite, if this is infinite, then you can, then there are no distinct integers such that G power m equal to G power n. Correct? Yes or no? This statement is true. This statement is true because I told you, because if this will happen, then this G will be finite. Yes or no? So these two things are, you already know these two things. So if, like, okay, let's assume m is greater than n. So let's assume m is greater than n. If this will happen, if this will happen, a power m equal to a power n, then it simply implies that order of a is less than equal to m minus n. Okay, so it means order of a is equal to finite. Now I can say if order, okay, contrapositive, contrapositive, what will be contrapositive? What will be contrapositive? Contrapositive will be that if order of a is infinite, then it means that we don't have, then, okay, then I can say, for any m not equal to n, this a power m is never equal to a power n. So this is just a contrapositive, because you know that if this will happen, then order of a will be finite. If this will happen, so if order of a is infinite, then for any m comma n, this will never happen. Okay, always a power m will be not equal to a power n. So tell me the answer for this question. Let G be a group under binary operation. You have some element, and this you already know. So basically, this is the subgroup generated by A. This is basically the subgroup generated by A. So can I say this is a subgroup? Yes, of course it is a subgroup. It is a subgroup. Now tell me, can I say this is a group? It is a subgroup, so this is a group also. It is a subgroup, so it is group also. So it is a group. So it is a subgroup actually. This is a, okay. So remember, this is a subgroup of G. Okay, so this is a subgroup of G. You already know. You already know this is subgroup of G. And this is generated by A. Subgroup of G generated by A. So yes, this is a group. Can I say this is cyclic? Can I say this is cyclic? What is the generator? Yes, what is the generator? Tell me, what is the generator? The generator will be G. The generator will be G. Array, just think about it. These things are not hard. You know what is cyclic group? This is the template of cyclic group. The cyclic group template is this. You have some element G, and cyclic group is nothing but G power 0, G power 1, G power 2. This is the template of cyclic group. G power plus minus 1, G power plus minus 2. This is the template of cyclic group. Okay, so this is the idea. You know, any cyclic group, this is the template. So any cyclic group you can write like this, G power integer. Okay, this is how you can write any cyclic group. This is the template of any cyclic group. Now notice that if you have any group, and let's assume that A belongs to G, then what is this? Then what is this? N belonging to integer. You know, this is a subgroup of G. I can say this is subgroup of G. I can say this is subgroup of G. But you can also notice individually this is a group. Just think individually. Individually, this is a group also. If you notice individually, just notice individually, this is a cyclic group. Can you notice this is individually a cyclic group? Can you notice? Individually, it is a cyclic group with the generator equal to A. A is the generator. So individually, this is a cyclic group. Individually, this is a cyclic group with a generator A. Let me take one example so that it becomes clear to you. Consider this example. You have this set of integers, comma addition. Now, this 2 belongs to set of integers, right? What is subgroup generated by 2? What is subgroup generated by 2? That will be all the even numbers. Subgroup generated by 2, that will be all the even numbers. So you can notice, yes, this is a subgroup. You know, this is subgroup of Z. I can say this is subgroup of Z. Okay, now tell me, is this a cyclic group? Individually you think. Okay, individually, is this a cyclic group? Now just think about this. Okay, so just think about this 2Z, comma addition. Can I say this is a cyclic group? Can I say this is a cyclic group? The answer is yes. Okay, and who is the generator? The generator is 2. So individually, if you think, then this is a cyclic group. Can I say 2 is a generator of this group? Can I say 2 is a generator of this group? The answer is no. 2 is not a generator of this group. So remember, 2 is not a generator of this group, but if you individually, if you take it outside. Okay, so this individually, this is a cyclic group with a generator 2. For this is the generator. Is this concept clear? So I can say 2 is not a generator of this group, but I can say 2 is a generator of this group. 2 can generate this group. So 2 is a generator of this group. So this is what I'm saying. So I can say that, yes, this is a cyclic, because this is cyclic group and this is subgroup also. So I can say this is a cyclic subgroup of G. And this subgroup, this is always cyclic. If you notice, for any group, this is always cyclic. For any group, whatever group you take, is this clear? Whatever group you take, this is always cyclic. This thing is always cyclic. So I can say this is a cyclic subgroup. Okay, so this, remember, so that is the reason this is called cyclic subgroup. So remember, this is called, this is, the name is this. This is called cyclic subgroup of G generated by A. Of G generated by A. Because this is individually, remember, individually this is cyclic group. Okay, is this concept clear? So I can say this is known as cyclic subgroup of G generated by A. So these two words are same. Remember, these two words, they are same basically, because any group you take, then I can say that, and any element you take, any element, then remember, for all elements I can say these are the names. This name you can give, subgroup of G generated by A. You can also give this name. You can also give this name cyclic. You can also give this name cyclic subgroup of G generated by A, because this thing is always individually cyclic. Okay, so this is individually a cyclic group. Okay, so cyclic group versus cyclic subgroup. Yes, this is the difference. Cyclic group versus cyclic subgroup. So understand the difference. Understand the difference. For example, I can say cyclic group means a group with generator. This is a group with generator, with at least one generator. So this is a group with at least one generator. And this is cyclic subgroup, means this is a subgroup. This is a subgroup which is individually cyclic, which if you see if you see individually, if you look individually, okay, which if you look individually is cyclic. For example, this example, please understand this example. You can notice this is not a cycle. You can notice this 2 is not a generator. This 2 is not a generator. But if you look at it individually, then you can notice this is a cyclic group. So what can I say about this? Finally, what can I call it? I can call it cyclic subgroup of Z. I can call it cyclic subgroup of Z generated by 2. I hope this point is clear. So tell me, is this difference clear? Cyclic group means a group with at least one generator, and cyclic subgroup means it is a subgroup which is individually cyclic. So you can notice. And can I say this is abelian? Can I say this option C? Can I say this is abelian? Yes, this is abelian also. Every cyclic group is abelian. Every cyclic group is abelian. Okay, because you know every cyclic group is abelian. Every cyclic group is abelian. And what about this last one? This last one. If H is a subgroup of G and H contains G, then can I say this is subgroup of this? Think about it and tell me the logic. This statement is also correct, but what is the logic? The logic is very in a small detail we have already seen. The logic is in a very small detail that we have seen. Basically, this is saying, okay, this statement, if you notice this option D, this option D is saying that, so H is a subgroup of G and G belongs to H. Then can I say that this is a subgroup of H. This is subgroup of H. First of all, what this means? This means H is a subgroup containing G. This means H is a subgroup containing G. Right? Yes or no? H is a subgroup containing G. Agree or not? This means H is a subgroup containing G. And what is this? And tell me, what is this? What is this? This is a subgroup. This is the smallest subgroup containing G. This is the smallest subgroup containing G. Okay, yes or no? This is the smallest. This is the word we have many times I told you, but you might have forgotten this. This small details. This is the smallest subgroup that contains G, containing G. So from these two, what can I say? Is this clear? Remember, H is a subgroup that contains G, but this G is a, for example, it's like this example you take Z comma plus. Here, can I say Z is subgroup of Z? So here, can I take H as Z? You can notice, yes, H is a subgroup of Z. So I can take H as Z. And you can notice, what is this? This is equal to 2Z. This is equal to 2Z. So you can notice, this is the smallest. Remember, this is the smallest subgroup of Z containing 2. Correct? Yes or no? This is the smallest subgroup of Z containing 2. So I can definitely say that this is a subgroup of H. So this is the idea. Is this clear? So this small detail, on this small detail, this question.